Hello, everyone. Welcome to today's current seminar. Today we have three speakers, T-Talks, all of them from the same group and same university. They are all from University of California, Irvine, and they are working with Professor Amin Bostanova. The first speaker is Carlos Mora. He will be giving a talk on a Gaussian process framework for operator learning. Carlos Mora is a fourth-year PhD student at the University of California, Irvine, specializing in scientific machine learning, data fusion, and uncertainty quantification. He is the recipient of Balcells Fellowship, which is awarded to students with exceptional academic performance to pursue graduate studies in the United States. Prior to his PhD, Carlos graduated in aerospace engineering with honors from the Polytechnic University of Catalonia. With that short introduction, you can start your presentation.
Right. So thank you, Nas, for introducing me. So today I'll present and I'll focus on my two most recent projects, which consist on a Gaussian process framework for solving PDEs and also operator learning. So this presentation will be divided into two main parts, each of them corresponding to each of those works. So the first part corresponds to the first work, and it essentially consists in a GP-based approach in which we leverage neural networks as the main function in order to learn and solve PDEs. The main feature of this approach is that thanks to its kernels, it can automatically satisfy the BCs and the IC, as well as possibly other linear constraints acting upon the solution. And lastly, another interesting feature of this model is that anyone can use any differentiable function approximator in its mean function. Then the second part of the introduction of the presentation, will be regarding our GP-based framework for operator learning. And here we actually introduce also a hybrid GP-NN-based framework for performing data-driven operator learning. But if the physics of the problem are also available, this model can also leverage this. And as I will discuss later, this method also introduces the first zero-shot mechanism for operator learning. And when I say zero-shot, I mean that it requires no training at all under some specific conditions for obtaining a decent performance. And lastly, one more insight that I will provide in this second part of the presentation is that GPs with traditional kernels, such as, for instance, the RBF kernels, were always known to suffer from the so-called curse of dimensionality. But one thing that we observe in this group is that they actually can handle larger dimensional inputs than we previously anticipated. So the first work lies within the field of physics-informed machine learning, or PML for short. And as you all know, this field has gained a lot of popularity in the recent years, mainly because it promises a unified platform for solving forward and inverse problems which involve PDEs, quantifying uncertainty, and also simulating data together with the physics of the problem. So in this field, we find two clearly distinguished classes of methods, one which relies on neural networks or NNs, and then the second class of methods relies on Gaussian processes or GPs. These GPs have some attractive features such as their simplicity, interpretability, as well as their natural ability to quantify uncertainty, but they also come with some disadvantages that need to be addressed somehow. So here I'm bringing up a fragment from a paper, from actually the introduction of this paper, which is an introduction to Gaussian processes. And at the beginning of this paper, it seems that the author is actually promoting neural networks over Gaussian processes, although it is a paper about Gaussian processes. However, as you start reading more and more into it, the author starts bringing some of the attractive features that arise from GPs and when and why should these models be used. So in that similar spirit, what I would like to argue in this presentation is that instead of confronting these two models one against each other, why don't we bring the best from both worlds in order to solve PDEs? And that is actually the main motivation for our approach, which we have coined as neural networks with kernel-weighted corrective residuals, or NNCores for short. So before jumping onto our approach, I would like to quickly go over how we can solve a simple PDE such as the 1D viscous Borges equation by using neural networks in the framework of pins. So you are all more than familiar with this. So, but I would like to quickly bring two things here. The first one is that we have to build a multi-term loss function, basically by leveraging automatic differentiation. And then this loss function contains like three different terms, each of them corresponding to the PDE residual, the BC, and the IC. Now, there are two main issues that arise from this loss function. The first one is that the BCs and the IC are not hardly imposed. And then as a consequence of that, we don't really know what's the best strategy of the optimal strategy for balancing each of those terms right here. And these issues have been addressed in multiple works, and I will compare my method to these works later on in the results section. Now, let's move on to the other side of the spectrum that we had before. And let's also try to solve the same PDE by using now a Gaussian process, or GP. So we start simply by placing a GP prior on our solution U. And this GP contains a mean function M, which is parameterized by theta, and a covariance function C that is parameterized by phi. For the rest of the presentation, you can assume that this covariance matrix is the Gaussian kernel, and hence the phi parameters are the length scale parameters. Now, to estimate these parameters phi and theta, we actually need to generate some input-output observations somehow. So if we go back and look at our PDE system, it turns out that we can actually generate very easily some samples from the two bottom equations, which correspond to the BC and the IC. And the good thing is that because we're provided with the equation, we could generate as much data as we wanted from these two equations. Now, we know that linear transformation of a GP is still a GP, but unfortunately, the first equation of this PDE system is nonlinear on U. And hence, we cannot directly apply a GP to it unless we directly discretize or linearize, sorry, this equation. So for now, let's forget about the first equation, which is the PDE system, the PDE, and then let's focus on simply generating samples from the two bottom equations. So I'm denoting the collection of inputs and outputs from this data set as capital X and little u. And for now, let's assume that we have already found a way of estimating these parameters theta and phi. And I will come back to that later. But for now, assume they are already estimated. So now, if we wanted to simply make some predictions at some query points X star, we could use the formula of a conditional mean GP, which reads as follows. And this formula is actually composed by two terms. The first one, which essentially is the mean function, and the second term is the or what we have coined as the kernel-weighted residuals. And this equation is the main motivation behind our approach. And as I will show later, this equation has some desirable properties for solving PDEs. And I will use in the next few slides a very simple regression example based on sinusoidal examples in order to show that. So now simply consider the simple task of approximating this simple sinusoidal function given some label data that has been generated from this underlying function. So there are three important features that arise from this equation right here. The first one is that it heavily relies on the mean function for data scarcity scenario. So in these two examples here, I'm representing my training data with these red crosses, and we can see that they are concentrated close to the boundaries of the domain. Now, we see that as we try to make predictions farther away from these samples, our conditional GP suffers from what is known as the reversion to the mean, right? So in that case, I'm using a zero mean or a mean function, which is actually the solution, right? Now, the second important feature to note from this equation is that if we have sufficient data across the entire domain, the conditional GP can actually learn the target solution very accurately, even for suboptimal choices of the kernel and the mean parameters. And this is a direct consequence of the third feature, which is that this conditional GP can interpolate our training data, which in the context of PDEs is the BC or the IC, regardless of what we use as our mean function. So if we put all those things together, essentially what this suggests is that a GP with a flexible and differential mean function provides an attractive prior for solving PDEs because of these interesting features. And now I will delve more into the interpolation capabilities of the GP with another example. So let's say that, again, from this same sinusoidal function, we now generate a very dense set of labeled data from this underlying function, as I'm showing here again with some red crosses. And now we simply proceed to plot the L2 error of the mean of the conditional GP as a function of our length scale parameter phi. Now, what we observe here is that rather than having one optimal value that enables to interpolate the target solution, we actually found that there is a range of values that gives this accurate interpolation. And the reason for that is that we simply have so much data that we simply need to pick a value for this length scale parameter that allows the kernels to capture the spatial correlations while ensuring that the covariance matrix is not ill-conditioned. So again, if we go back to the context of PDEs, what that essentially means is that because the BCs and the IC are generally given equations, we can generate as much data as we want, and hence we can simply proceed to pick a length scale parameters that ensures this accurate interpolation in the boundaries and at t equals 0. So essentially, we can simply fix this length scale parameter, and this will allow us to avoid inverting the covariance matrix in each step of the optimization. And this will also help to alleviate the numerical instabilities that arise from jointly optimizing the NN and the kernel parameters. And I will delve more into the details of this second point now in the next slide. So this is my last pedagogical example for showing the motivation of our approach. And again, I'm considering another the same sinusoidal example. And now I'm generating only some data points on the boundaries. And now I'll proceed to fit 3 different models. The first one is a zero mean GP whose kernel parameters are simply estimated via MLE. Then I have a GP with a neural network as its mean. And I also proceed to estimate its kernel and mean parameters via MLE. And now I have a third model, which is again a GP with NN as the mean function. But now I'll proceed to simply fix the length scale parameter to ensure interpolation in the boundaries. And then I'll proceed to estimate the parameters of the neural network via some physically informed loss function, which in that case is simply the error on satisfying this ODE right here. And these are the results that we obtained. Here I'm showing the condition number of our covariance matrix by kappa. So we see that in the first case, our zero mean GP reverts to the mean as we move farther away from our training data. We see that if we include a neural network as its mean function, this is slightly elevated. But it turns out that if we proceed to simply fix this length scale parameter and estimate the mean parameters based on a physics loss function, then we can actually learn the solution across this entire domain while keeping the condition number as low as possible. So the main takeaway here is that if we use an NN mean GP for solving PDEs, we can actually fix the kernel parameters to ensure the accurate interpolation of BCs, ICs, and possibly other linear constraints. And then we can optimize the mean parameters data based on the PDE residual. So all these insights that I have been giving now are the main core motivation of our approach. And I'm describing that here through this flowchart right here. So I'm dividing the flowchart into 2 different models or steps based on these insights. And then the first model essentially consists on, as I started this presentation, by placing a GP prior on U. And then because we can generate as much data as we want from the BCs and the IC, we can simply fix the kernel parameters to some value that enable interpolation in this. And then once we're done with model 1, we simply have a GP that is able to perfectly give predictions on the boundaries and at t equals 0, but doesn't make accurate predictions inside the domain. So that is why in model 2, we now proceed to estimate the parameters of the neural network by conditioning the posterior GP on the nonlinear PDEs. And this framework has the several advantages. The first one is that thanks to the kernels, we can actually reproduce perfectly the boundary data. It can also adapt to any topology. And also the GP-based formulation provides a natural way for handling noise. As a direct consequence of one, actually this framework also facilitates the training of the neural network, since these now then have to take into account for the error on the BCs or for the IC as well, and only have to minimize the PDE residual. And we actually provide a proof in the paper for points 1 through 3. So we performed several numerical studies for 4 different benchmarks, which are the 1D Burgers equation, the lead-driven cavity problem, which is governed by the Navier-Stokes equations, a nonlinear elliptic PDE, and the Aconal equation. For each of these four problems, we actually tested two different values for its coefficients in order to give rise to different levels of complexity in the solution. We also compare our method against four different PIML models. The first one, which is an optimal recovery approach, which leverages zero-mean GPs. The second one is vanilla pins, and the architecture of these vanilla pins is the one that we exactly use as the mean function of our GP-based framework. And then the other two last models are two variations of pins, one which essentially balances the loss components in a dynamic way. And then the fourth one is a pin whose output has been designed to strictly satisfy the basis or the IC. And for each of these two problems, we have also tested different capacities for the network that is used in the NN-based approaches. And across all these problems, we observed that actually NN course achieves the lowest error. And also more interestingly, we also can see that even in some cases, the smaller architecture achieves a better performance than the larger architecture of the other NN-based approaches. We also performed some additional studies where we analyzed the effect of the network that was used as the mean function, as well as the number of collocation points. And in both cases, we observed that thanks to the kernel, NN cores can achieve smaller errors with both smaller networks and as well less number of CPs. And we also analyzed the effect of optimizer, randomness, and also the architecture type that is used in the mean function. So for instance, here, we were using as the mean function the M3 architecture that was originally developed in reference 1. And we actually compared that against its vanilla implementation, which is denoted by M4. And in that case, we also observed that when we wrap this architecture around our GP-based framework, we achieve lower errors. We also studied the effect of adding noise to the boundary data, and we observed that the method can still provide accurate predictions for two different levels of noise. And lastly, the model can also address inverse problems by simply adding the coefficient of the PDE as an additional parameter in the optimization loop. And as we expected, so the convergence rate is faster as we have more labeled data inside the domain. So in this first part of the presentation, I have introduced NN course, which is a PIML model that leverages the strengths of neural networks and kernel methods for solving and learning PDEs. And Amin will show later an application of this method in the context of topology optimization. We have also shown its robustness by analyzing the effect to the optimizer, randomness, and also corrupting the BC and the IC data with noise. This method can also address inverse problems by simply adding the PDE coefficient as an additional hyperparameter in the loss function. And then, as I said at the beginning of the presentation, this method can leverage any differential function approximator as its mean function. And here you can find the QR code for its code and as well as its archive version. And this has been the end of the first part of the presentation, so I'll be happy to take any questions regarding that part, since some of the things that I have explained will also apply for this second part.
Thank you so much for your great talk. Do we have any question for the speaker from the audience? Yes, Matthias. Can you introduce yourself first?
I'm Matthias Erhard, University of Wuppertal from Germany, professor of applied mathematics. I have just a quick question. So did you check the case when nu is equal to 0? So when you have a pure hyperbolic PDE and shocks may appear?
Yeah, we actually tested that case as well, and we ended up using as our mean function another architecture that had been developed for addressing this type of shocks that arise when nu equals 0.
Okay, so, thanks.
Yeah. Yeah.
Do we have any other questions for the first speaker? So I think there is no more question. Are you ready to move on to the second presentation? Yeah, go ahead.
A little bit longer than the one from my colleagues. So now we'll start with the second part of my presentation, which now consists in an operator learning approach based on Gaussian processes. And this work is a collaboration with Professor Hosseinmardi from Caltech. So I'll start by defining some of the notation that I will use along this second part. So let's define two infinite dimensional spaces as calligraphic U and calligraphic V, and say that there exists some nonlinear operator G dagger that maps the infinite dimensional space to the infinite dimensional space V. And the formulation that I will explain now is for the case of single output operators, but this can easily be extended to the case of multi-output operators, as I will also demonstrate later. So in addition to that, I'm also defining two bounded linear operators such that they map the input and the output function to their discretized version, which is typically a very high dimensional vector. The vector corresponding to the input function has P components, and the one for the output function contains Q components. So in general, we can say that the overall goal in operator learning is to approximate this operator G dagger given some set of n pairwise elements, which are essentially the discretized versions of the input function and the output function. So as you all know, operator learning promises a unified platform compared to traditional numerical solvers, mainly because it's more computationally efficient, at least in inference. And due to that reason, there has been a lot of works that have been developed recently. Most of them are revolve around the use of neural networks architectures, and the most popular examples are DeepONet, FNO, CNO, or GNO, but there are many more out there. However, there has been a kernel-based method which has recently shown to be competitive, at least in the terms of the cost-accuracy trade-off, and this has been developed by Fuhrman's group. This method also inherits the nice properties of kernel-based methods, which are their simplicity, their interpretability, and their natural way to quantify uncertainty. So in this presentation, I will introduce an alternative to this method, which is also based on a GP formulation. And as I will show later, it's very easy to implement, and it also requires little to even no training under some circumstances. So the framework of our method can be easily explained through the diagram that I have right here. And so in the original operator learning problem, we aim to approximate this operator G dagger, which maps the infinite dimensional space U to the infinite dimensional space V. Unfortunately, the issue is that here, if we wanted to actually use a neural network or a GP for approximating this operator, we simply can't, because these are function approximators and not operator approximators. So in order to be able to use GPs, we need to actually rewrite this operator learning problem as a function learning problem, or also known as a regression problem. And so to that end, we start by writing its associated real valued bilinear form, which gives rise to the operator G tilde dagger. And this operator G tilde dagger is connected to the original operator G dagger through the equation that we see, the equality actually that we see right here. And so we can see that now we're dealing with a functional learning problem in which we are aiming to learn the mapping, which consists in taking an element from U, then an element from the dual space of V, and then we map it onto the a real value. Now, in practice, this input function needs to be discretized in order to be able to use it with computers. So what we end up having is actually a functional learning problem or a regression problem. And now in that case, we have to consider this operator or mapping G tilde dagger P, in which we're essentially mapping the discretized version of our input function, the location where we are observing our output function, and then we map that onto a real value. Now, all this work has been done so that now we can use a Gaussian process to approximate this mapping, which is actually a function. So we start by placing a GP prior on GP tilde dagger. And similarly to the first part, this GP has a mean function M and a covariance function C. And now the main difference with respect to the first part is that now I'm using beta to denote the length scale parameters, and also sigma squared to denote the variance of the kernel. So now that we have reformulated the operator learning problem as a regression problem, we can now proceed to do the standard procedure for estimating its parameters, which in that case, we're simply using maximum likelihood estimation, or MLE. But to that end, we need to actually reorganize our original data set, since now we're also accounting for the location of the where we're observing the output functions. So actually, the price that we have to pay for reorganizing this data set is that now we're increasing its size from n to nq, right? Where n is the number of samples that we originally had, and q is the resolution of our output functions. So I'm denoting as capital bold X the collection of inputs from my data set, and as bold little v as the collection of all the outputs that I have in my data set. So now we can simply write the typical minimization problem that arises from MLE, where capital bold C is the covariance matrix, and this is an NQ times NQ matrix. And as you can imagine, and the reason for which I'm highlighting that in red is that because these numbers can easily become extremely large, and so the issue not only becomes to invert this matrix, but also even sometimes we cannot even build that matrix C. So we need to somehow address that. And the way we're addressing that is by leveraging the Kronecker product. And to be able to do that, we need to make two assumptions. The first one is that we're assuming that the observation operator doesn't change across samples, and that essentially means that the locations where we are observing the output function remains the same across samples. And then, as the second assumption is that we also need to adopt a separable kernel. And by that, I mean that we need to split our original kernel into the multiplication of two kernels. The first kernel essentially takes the discretized version of the input functions, and the second kernel takes the location where we're observing the output functions. And I'm denoting their parameters respectively with the subindex phi and subindex y. So by using these two assumptions, we can now rewrite the covariance matrix as the Kronecker product of these two smaller matrices, C phi and Cy. C phi takes into account the correlation between all the discretized input functions that we have in our data set, and Cy takes into account the correlation between all the locations where we are observing the output function across our data set. So this Kronecker product comes in very handy because now we can leverage the properties of Kronecker product in order to rewrite the minimization problem in an efficient way. So this reads as follows, and now we can see that we're only computing the determinant and the inverse of these two smaller matrices, which are Cy and C phi. So this is the general loss function that one could potentially use for training a general GP by using this loss function. But however, now we'll develop two more specific strategies that are justified by the nature of the operator learning problem. So first of all, if we assume that the observations in the output space are dense, then given what I explained in the first part of the presentation, we can simply fix our length scale parameter beta y, which is the length scale corresponding to the locations of the output function, to a large value. And as I will motivate shortly, the length scale parameters corresponding to the kernel that takes care of the discretized input functions, those will be initialized to small values. And that is a direct consequence of having very high dimensional vectors as inputs. So the strategy is the following. So for zero mean GPs, we'll simply fix beta y to a large value, for instance, 10 to the power 3, and then we will initialize beta phi to a small value to make sure that our GPU will be able to learn those correlations in such a high dimensional space. For the case of non-zero mean GPs, we simply proceed to fix beta y and beta phi, as I mentioned previously, and hence we only end up training or estimating the parameters of our mean function. In that case, we're only left out with the second term, which we had in the original loss function, which is the data phi term. And one thing to note here is that if Cy and C phi were the identity matrices, that means that we're assuming that all our samples are independent from each other. Now this loss function would become the typical mean square error that is used for NN architectures in the context of operator learning. However, because these are not the identity matrices in our case, that means that we essentially have a modified version of the mean square error, which also takes into account the correlation between samples, which it's some sort of adding a regularizer to the problem. So as I mentioned previously, due to the high dimensionality of the discretized input functions, we need to promote smaller length scale parameters for beta phi. And I will motivate that with the following example. So for now, let's simply consider the Gaussian kernel, and let's write it as a function of the distance between two input vectors x and x prime. And for now, I'm assuming that the length scale parameter is shared across all the components of x and x prime. So now this allows us to simply solve for beta, and we get the following expression. And now let's conduct the following experiment. So let's say now that we want to know how does the histogram of beta looks for some fixed values of c, given that we generate a large number of samples x and x prime randomly from the unit hyperkey. And that is actually what we ended up doing here. So here I'm choosing two values of correlation, 0.2 and 0.8. And what I'm doing is that I'm generating the histogram of betas by increasing the dimensionality of these x and x prime. So we can see the following, that as we increase the dimensionality of these input vectors x and x primes, we observe that the histogram of beta not only shrinks, but also moves toward the left of the plot, which means that essentially it's concentrated around smaller values. So the main takeaway from this slide is that GPs with typical kernels such as the Gaussian kernel, they suffer from curse of dimensionality, yes, but this can be delayed if we promote smaller values for the length scale parameters. And this is why we initialize beta phi to small values such as 10 to the power minus 2 to ensure that equivalent correlations in such a high dimensional space. And the same conclusion can be reached through another point of view. So now let's again consider the Gaussian kernel with some functional inputs. So now these u and u prime are functions, but not vectors. And once again, let's now use this formula to justify this choice. So this norm that we see here is the L2 norm for functions, which can be numerically approximated. And now, if we assume that the discretization points are equally spaced across the entire domain, then we can simply plug in this result into the top equation, and we are left out with the following expression. So we see that now this Gaussian kernel looks very similar to the Gaussian kernel that could be used for vector inputs, but this time the length scale parameter is multiplied times the discretization step, which is generally small. So what that essentially means is that functional inputs naturally give rise to an effective length scale parameter, which we have called it as beta u, which is generally smaller than the original length scale parameter that we would use for vector inputs. So far, everything that I have been explaining in this second part was regarding approximating single output operators, but this can be easily extended to approximate multi-output operators. So now, instead of having one single output function, we have a large S output functions. And the goal is very similar to before. So we want to approximate this operator given a data set which contains the discretized input functions, the discretized output functions for all of them. And we also have an output indicator, which is S, in order to specify the output to which each sample is corresponding to. So following the same procedure that I followed before, we can simply place a multitask GP prior on GP tilde dagger. And the main difference now is that the kernel also now takes into account for this output indicator S. And we also adopt now a separable kernel in order to be able to leverage the Kronecker product in the loss function and in inference, as I will show. Now, this separable kernel is essentially the multiplication of 3 different kernels, 2 of them which are the same as we had previously for the single output case, but now we also have an additional kernel which takes into account for the correlations between the different outputs. Now, for the sake of simplicity, I'm simply assuming the identity matrix for these kernels that takes into account for these correlations. So what that essentially means is 2 things, at least from the eyes of the kernel, is that these outputs are uncorrelated, and secondly, that the variance of those outputs is the same. But these correlations can still be captured through the mean function. So now the general minimization problem that arises from MLE becomes this expression here. And it looks pretty similar to what we had for single output operators, but the main difference is that now the complexity terms are multiplied times the number of outputs that we have. And also now the data feed term accounts for the summation of all over the outputs that we have in our data set. And now we follow the same strategies for zero and non-zero means that I suggested before. So everything that I have explained until this point was regarding the training of the model for cases in which we had either single output or multi-output operators or zero and non-zero means in the GP. And now, once that we have been able to estimate those parameters by using some gradient descent-based optimizer, we can now do the predictions via the conditional GP formula given some test input U star and some query location Y star. And to that end, we can also leverage the properties of the Kronecker product in order to make these computations more efficient. Now, the interesting thing here of these two equations is that our predicted GP is also differential with respect to Y star for typical kernels. So what that essentially means is that if the physics of the problem are available, we can use that for also training our conditional GP. And here I'm expressing a general family of time-dependent PDEs as follows. And now in the context of physics-informed operator learning, the goal is, again, to approximate this operator G-dagger given a set of n pairwise observations and also the above PDE system. And in the context of physics-informed operator learning, I will be using non-zero mean functions, that is mean functions such as DeepNet or FNO, in order to be able to have more flexibility in the model and be able to leverage the physics. So similarly to how it is done in the PINS framework, we can now build the following loss terms by leveraging automatic differentiation. And we can now simply add them up to our data fit loss term. And here I have to mention that we need to also account for the BC and the IC terms, since the kernels that we have now in our model may not be able to accurately interpolate the BCs or the ICs, given that the test samples might not be seen, well, they're actually not seen during training. And each of the terms that we have in our loss function, they are weighted by some coefficient, which is obtained by the learning rate annealing approach that is suggested in reference 1. So in the context of single output data-driven operator learning, we have used the following 4 benchmark problems, which are the 1D Burgers equation, the 2D Darcy flow, the 1D advection equation, and the structural mechanics problem. And these datasets are not generated from us, but they are taken from other works and papers that I will cite in the next slide. So here I'm showing the summary of the result that we obtained, and we tested several variations of our approach, either with zero mean or non-zero means, as well as zero-shot, zero-mean functions. In that case, when I say zero-shot, I mean that we have not trained at all our model. And here I'm reporting the relative L2 error and as well the number of parameters. And we're comparing all of these models against DeepNet, FNO, and the GP-based approach developed by Human's group. So we observed 3 important things here. The first one is that the performance of the neural operators that we tested against improves as soon as they are used are the mean function of our GP framework. Also, we observed that the zero-mean GP achieves pretty small errors with many orders of magnitude less of parameters than its competing methods. And lastly, we observed that thanks to the proper initialization of the parameters that we suggested before, the zero-shot, zero-mean GP actually provides a decent accuracy with no training at all. And I will now provide some more insights on these aspects in the next slide. So here I'm actually showing the loss and the error profiles for the 1D Burgers and the 2D Darcy flow problems. And the left plots correspond to the loss profiles and the right plots correspond to the error profiles. And so in the loss profiles, we observe, first of all, that the loss function is minimized for pretty small values of beta phi, as we suggested initially. Then if we look at the error profiles, we observe that the error is actually minimized for a pretty broad range of values of the length scale parameters beta phi and beta y. And actually, they are consistent with what we observed before, is that beta y should be initialized or fixed to a large value, and beta phi should be initialized to a pretty small value. So what that essentially means is that if beta y and beta phi are properly initialized, we can actually have a zero-shot, zero-mean GP, which might not be the best model available, but it can be a very easy to implement and a good baseline model. So in the context of multi-output operator learning, we use the lid-driven cavity problem as our benchmark. And we generated, well, we actually took the data set from reference 1. And the way they generate the data set in this paper is that they take one instance of the lid-driven cavity problem, and then they sweep smaller windows in order to generate each of those samples. And then the mapping that is aimed to learn is the solution at the boundaries to the solution inside of each of those windows. And also what we have done is that we wanted to see what was the extrapolation capabilities of each of the models that we had. And to that end, what we did is that we divided the domain of this lid-driven cavity problem into two main regions, one which is the extrapolation region and another one which is the interpolation region. And I'm calling that by these names because our trained samples are located in this interpolation region. And then we can have test samples from either one of these two regions. But we don't have any training sample at all in this extrapolation region. And as you can expect, like this extrapolation region is closer to the lid, so it contains larger gradients, the ones that are seen during training. And we use a pre-course resolution because we'll use also the physics in order to train our model later. And we wanted to see if simply by using a coarse resolution, using the physics will be able to help us in achieving better predictions. So this is, again, the summary of the results that we obtained, where I'm also reporting the number of parameters for each of the variants of the models, as well as two neural operators. And I'm also reporting the error in both the interpolation region and in the extrapolation region. And within these two different regions, I'm showing the error obtained by training via MLE, which is the loss function that we actually propose for non-zero mean functions, or simply by naively using mean square error for training these mean functions. And we observe the following points here. So the first one is that we achieved the lowest error by using the DeepONet mean GP in both the interpolation and the extrapolation region. We also observed that using MLE for training our non-zero mean functions allows us to achieve lower errors in also both regions. And as we expected, the error from the interpolation region to the extrapolation region increases substantially, since this region contains much larger gradients than the ones that are seen in the interpolation during training. So here I'm reporting the training time in seconds per epoch for each of the approaches that we have. And this especially changes across different problems, since it really depends on the dimensionality and the resolution of the problem. But in general, we could say that training neural operators within our GP framework is more expensive than its vanilla implementation, mainly because we have to also do computations for our kernel. But it comes at the, we believe it's worth it because we achieve higher accuracy by wrapping it within the GP. And lastly, I would like to show the results on the physics-informed version of our approach. To that end, we use the one-dimensional Burger's equation with Dirichlet boundary conditions. And we also use a pre-course resolution for the output function, in that case, a 12 by 12 grid. And this is because we expect the physics of the problem to help us to better learn the solution within these sparse samples. And here I'm showing the results or the visualization of the results for our DeepONet mean GP. And this is just for one of the particular examples that we have in the test data set. And we observed that, as we expected, adding physics to the problem helps in improving the accuracy from only having data. And the last example that we use for testing our physics-informed version is the two-dimensional lid-driven cavity problem, in which, again, we are also learning the mapping from the solutions in the boundaries to the solution inside the domain. And so we perform the following convergence study for these two problems, one for the 1D burgers and the other one for the LDC. And we tested several neural operators as well as our model by using only data and using data plus physics, which are represented by the dashed lines. And we observed that in overall, adding physics helps to reduce reliance on data. And as well, we observe once again that when we wrap those, in that case, DeepONet as the mean function of our GP, we achieve higher accuracy than when the DeepONet is used standalone. So in this presentation, we have introduced a hybrid GPN-based framework that can perform data-driven or physics-informed operator learning. This model also gives rise to a zero-shot mechanism for operator learning in the case in which the parameters of the zero-min GP are properly initialized. And we address the computational bottlenecks and also the high dimensionality of our features by leveraging the Kronecker product and also promoting specific values that enable the kernels to learn those correlations in such high dimensional spaces. We believe that some interesting directions for future research are developing specific kernels for functional inputs or also making our approach resolution independent. The paper is already available on arXiv and the code will be available soon. I would like to thank my lab mates, Shirin Hosseinmardi, Amin Yousefpour, as well as Professor Hosseinmardi from GatTech and my advisor, Amin Bostanabat, as well as the funding agencies that have supported us. Thank you all for listening, and I'll be happy to take any questions that you may have. Thank you.
Thank you so much for the second presentation. So do we have any questions from the audience for the first speaker? I don't see anybody raising hand, so I think we can move on to the third presentation, second speaker.
Thank you.
So, yes, thank you so much. And can you stop sharing? Yes. Amin, can you try to share your screen? Presentation mode, please. Yes, great. Our second speaker is Amin Yousefpour. He will be giving a talk on topology optimization via physics-informed Gaussian processes. Amin Yousefpour is a PhD student in the Mechanical and Aerospace Engineering Department at the University of California, Irvine. His research is focused on scientific machine learning, inverse problems, probabilistic surrogate modeling. He holds a master's degree in mechanical engineering from the University of Tehran, where he specialized in vibration and control. With that short introduction, the floor is yours and you can start your presentation.
Thank you, Naz, for introduction. Hello, everyone. I'm Amin, and today I want to present our recent work on physics-informed Gaussian process for simultaneous and mesh-free topology optimization. Topology optimization provides a principled mathematical approach for designing a structure while satisfying set of constraints. In the literature, some methods have been proposed for topology optimization. The most famous one is solid isotropic material with penalization, or SIMP. The way that SIMP treats the topology optimization is with a density function, and this method directly tries to design the density function for different part of the domain. Another method is level set approach. Level set approach, which works with a function to define the boundaries between different phase of material. As you can see here in the right-hand side, this function, when this function is equal to 0, we have boundaries between different phase of material. And when it's negative, we have one phase of material. And when it's positive, we have the other phase of material. Also, in the literature, evolutionary algorithms have been used for topology optimization. This method usually uses genetic algorithm, and they are useful when we have multi-objective problems like urban planning. Topology optimization, and in particular SIMP, can be formulated as a constraint optimization. For this constraint optimization, we have objective function. This objective function is defined based on the state of the system, and it can be minimizing compliance in solid mechanics, or dissipated power in fluid mechanics, or even maximizing thermal conductivity. We define our objective function using U, which is a state variable of the system, and define the physics of the system, these variables, and density function rho. Also, we should satisfy a set of constraints. C1 here is our volume fraction, that we should satisfy certain volume fraction. And we have all other design constants, Ci, I'm showing here. And this density function ideally has a binary value. It could be either 0 or 1. The way that SIMP solved this problem had three main steps. At first, SIMP discretized the design domain. So instead of having rho, which is function of X, we have vector of rho. Also, SIMP worked with intermediate variables. Here I'm calling it rho tilde. And rho tilde have continuous values between 0 and 1. And then using penalization function, G, make the intermediate value of the rho density function to the binary values that is desired for design. And finally, SIMP solve a nested optimization. To see how SIMP work and solve this nested optimization process, let me walk you through the process. At first, we have some initial density and design domain. In an analysis step, usually we are using numerical method, numerical solvers, for example, finite element method. We solve some PDEs which define the physics of the problem. Having states of the equation, having state variables, we define objective function and sensitivities. By having sensitivities and objective function, we update our density vector, which is rho. We continue this process until convergence. So we are working with a nested process, and in each step of this optimization, we should solve the PDE system that govern the physics of the problem. So this method is nested, and sometimes it's computationally very expensive. Also, as I will show later in this presentation, they are sensitive to the initialization, and changing initialization can dramatically change the result. And because of the meshing process that we are using in the analysis step, usually they are sensitive to the function that we are using, and we need some filter to make the method stable and have a smooth result. To address all of these issues, we propose our simultaneous and mesh-free approach. We try to solve the PDEs along with other terms in optimization. So we optimize the topology while solving the state variables. This gives the model a built-in continuation nature and helps to capture the global optimum instead of being trapped in local minimum or optimum. Also, because we are not using any meshing in our method we don't have any checkerboard pattern in our method, and we don't need any filtering. Here you can see the flow chart of our method. At first, we have some initial parameters and design domain, which includes boundary condition. We defined a physics-informed Gaussian process. Output of this Gaussian process is density function and all state variable of the system. Having all of them, we define objective function, and we continue this process until final convergence. So now the question is, where and how Gaussian process comes to the picture? Well, I have vector of variables which include U, a state of equation, state variables, and density function. I place a GP prior on all of them, that is Z, and this GP has some parameters, zeta. Zeta includes parameter of the kernel and my mean function. So by having this formulation, my topology optimization became this constant optimization, this constant problem of optimization. So here the major difference with SIMP is we are including a state equation. R here shows a state equation. So we have them as additional constraint for our optimization. Also, here a state equation, they are not no longer a function of X and rho. They are just function of X. So we have this optimization and Gaussian process. The way that we are solving this optimization, simply we are using penalty method. Mu p here shows our penalty factor that we multiply constraint by it and add it to the loss function. So we will have augmented loss function. Also, for different terms in our loss function, we are considering adaptive weight. This adaptive weight helps us to don't let any term in the loss function dominate the whole loss. And the way that we are working with adaptive weight, I will explain in a little bit. So now one may ask why we are using Gaussian process and why we need Gaussian process to solve this simultaneous topology optimization. As Carlos mentioned earlier, when we are using Gaussian process, we can find a posterior for that automatically satisfy all boundary conditions. So we are using expected value of the GP, which include the information from our boundary conditions, and automatically we are satisfying all boundary and initial condition. The same formulation is used for density function, just we have some function G to make them binary, close to binary. So this is necessary for the built-in continuation that we have. Because if we don't solve, because from the very beginning, if we don't satisfy boundary condition, the results of and solution that we are getting for PDEs are not valid. And when they are not valid, they are not effective. So we are losing the effectiveness of, when we don't have this structure, we will lose the effectiveness of simultaneous approach. Schematically, it is how we are combining different terms in our model. We have a neural network which is shared between all variables and density function. The reason that we are considering a shared mean between all of them is to better capture dependencies between variables and density function. Also, we are using independent kernel for each variables and density function. This way, we can better manage and handle different boundary conditions that we have for each variables. For example, we can have some information about some state of the state variables and some information in other boundaries about density function. And this way we can handle all of them. Also, numerically, this method is more efficient because instead of having a big matrix, we have several small matrices, and we can easily calculate their inverse. To efficiently estimate the parameter of the system of our Gaussian process and be stable during the optimization, we are taking 3 steps. First, as Carlos showed, we can easily use for our Gaussian process, we can fix the parameter of the kernels. This way, we are numerically more stable and we prevent any ill conditioning that can happen during updating parameter of the kernel. So the optimization narrowed down to estimating the neural network parameters. We just need to estimate and update in each step of optimization just parameter of the neural network. Also, we are using finite difference to calculate gradient in the loss function. In the loss function, because of the residuals of PDEs, which define the physics of the problem, we have some gradient. Our model is flexible and we can use both finite difference or automatic differentiation. Later on in this presentation, actually toward the end, I will show when we are using automatic differentiation, we are getting more accurate results, but the price for this accuracy is lower or is more computational cost. Also, as I mentioned, we are using adaptive weights, which consider one term in the loss function as a reference and update the other ones in each step of optimization to don't let them to dominate the loss function. So we are not the first to use machine learning for topology optimization. In the literature, other researcher has used machine learning for topology optimization. One of them is Entopo, which used 2 neural networks. And they have 2 neural networks. One is for displacement and the other one is for density. Having 2 neural networks simplify the training, but still they have nested approach and its disadvantages. Recently, deep energy method have been proposed. Deep energy method that avoid to train displacement network and take advantage of self-adjoint property of compliance minimization and just have one loop, not nested approach. But this method is limited for the cases that we can define potential energy. And when we cannot define potential energy, we cannot use them. Also, recently, HPNs have been proposed in the literature for topology optimization, which use some hard constraint to solve the problem. In this study, they have considered the same problem that we are solving, but we are not comparing our result with this method, and we are comparing with COMSOL, which is way more competitive. The problem that we are considered to test the performance of our method is minimizing the flow's dissipated power subject to the volume fraction. The problem is defined under the incompressible flow assumption for Newtonian fluid. And I'm going to directly take the problem formulation from the reference paper. We have 2 momentum equations, one in X and Y direction. And also we have continuity equation. The goal is to minimize dissipated power, which is defined based on the drag and viscous forces. The parameter that define the different phase of material here is our rho density function, and it has a direct relation with permeability. In the literature, several equation and function have been proposed to connect permeability and density function. Here I'm bringing two of them. The reason that I brought two is that we are comparing our method with COMSOL, and COMSOL is sensitive to this choice. And our analysis shows that when we are using the second one, COMSOL result is more stable. I'm considering 4 different boundary conditions for this problem, and the goal is to see by changing boundary condition, our method is able to find the optimal topology for this equation. Also, as I mentioned, we are comparing with COMSOL. COMSOL is working based on SIM, and we consider random and constant initialization for COMSOL. And our analysis shows that for each of these cases, we should slightly change the setting for COMSOL, which is not the case in our method, and I will explain in detail in a little bit. Here you can see the evolution, topology evolution of our method. At first, the objective function is high. After few iterations, objective function sharply drops, and then it goes up. Around 10K iteration, our model is able to capture the physics of the problem and acceptable topology. After that, model spend times to refine the topology. As we can see here, in both cases is the same, and we can see the same trend in objective function. On the right-hand side, you can see the result from COMSOL. As I mentioned, COMSOL is sensitive. COMSOL is using SIMP, which is nested approach, and it's sensitive to the initialization. On the top, you can see the result of COMSOL when we started with a constant initialization. But when we are using start with random initialization, in most cases, we are getting some local minimum, and we are not, this COMSOL is not able to get global minimum. For other example, two other example, pipe bend and diffuser, we can see our model is able to capture and estimate the topology, which is close to what COMSOL is giving us. Another point about COMSOL is that for some problems, we forced to use filters. Otherwise, COMSOL is not stable. For example, here for pipe bend, we should use filters. Otherwise, we cannot any stable result. For diffuser, we didn't use it because when we are using filters, the efficiency of the model is lower, and we will get higher objective function and dissipated power. To compare our model in detail, I'm providing result median value for 10 repetition. We compared the dissipated power of our method with COMSOL in 2 initialization, random and constant. Comparing dissipated power with what we are getting from COMSOL, we can see they are in close agreement, except for rugby ball example, which our method has the upper hand. Regarding time, we cannot directly compare our method regarding computational cost and time with COMSOL, because we are using Python and GPU, while COMSOL is using CPU and implemented in C++ and Java. But I'm comparing time here to show that we are not by order of magnitude slower. Especially when we consider effect of initialization, we can see we are able to get computational costs in the same range as COMSOL. Also, we imported our topology that we are getting from our model in COMSOL and calculated dissipated power. Here I'm showing it with JC, and if we compare these values with value that our model is giving us, they have the same values in the same range, which I will explain why we have done this in a little bit in next slide. To gain more insight about our model and its dynamic, we compare different terms of the loss function. Here we can see the volume fraction. Our model is able to maintain below 10 minus 3 for volume constraint, and also for some cases even lower than this value as it is shown here. For COMSOL, the constant for volume constant is around somewhere between 10⁻5 to -4 for all cases. Other terms in the loss function have been shown here. As we can see, for the total loss, at first we have some increasement. After a few epochs, we have increasement. The reason for this increasement is because we are using penalty terms, and by nature it's growing, so it's add some values to loss function. Comparing the second row shows the residual for a scale value. R1 is residual for X, and R2 is residual for Y direction, and R3 is a scale value for continuity equation. When we compare them with non-scale values, for R1 and R2, we just have penalty term. But for R3, we have which is continuity term. We have penalty term and weighted that we are using from our Adam-inspired method. So now one may ask, still we have high residual, especially for R1 and R2. So can we trust the topology that we are getting from our model? Because still we have high values for these residuals. To answer this question, let's look at the contour of the residual from our model. And here I compare them with finite element method, the residual that we are getting for diffuser problem. As it is shown here, in our model, the average values is higher than finite element because we don't have any localized feature in our model to capture localized feature. But in finite element, locally speaking, in interface of solid and fluid, we have higher residual when we are using COMSOL. And also I have shown that the dissipated power we are getting from our method when we are getting from our method and when we import topology in COMSOL, they are in the same range and they have the same accuracy. So we can trust our method because topology, the results, the dissipated power from our method in COMSOL have been in the same range. As I mentioned, our method is flexible and we can use finite difference and automatic differentiation. When we want to use finite difference to calculate gradients, we are not using any meshing, just we are using finite difference to calculate gradients. So when we want to use finite difference to calculate the gradient, we need to collocation points be on regular grids. But for when we are using automatic differentiation, they can randomly be generated. Here you can see the result when we are using finite difference and automatic differentiation. Comparing dissipated power, when we are using automatic differentiation, we are getting better result, a slightly better topology because we have lower dissipated power. And in terms of residual, our model with automatic differentiation is able to have more accurate result and lower values for residuals. But the price for this accuracy is computational cost. When we are using automatic differentiation, we are 3 times slower than we are using finite difference. And all results that I provided in the previous slide are based on finite difference. In conclusion, we introduce a framework that integrates the strengths of neural network and kernel-based method. Our method has several advantages. As I show in the result, compared to COMSOL, we are robust to the initialization, while COMSOL is not robust and changing setting and initialization can affect the result dramatically. We don't use any meshing process in our method, so we are mesh-free and we don't need any filtering to make our model stable and have smooth patterns. Comparing dissipated power with our model and what we are getting from COMSOL, I show that we have a high accuracy. So as I mentioned, now our method don't have any localized feature to capture localized feature in the domain. And also for topology optimization, sometimes we have some information about the domain. So in the next step, we are working on this to capture localized feature of the domain. Also for convergence, we could finish the process at 10K iteration because we almost get the topology, but we continue until 50K to don't cherry pick. So we are working on a systematic process to assessment convergence and terminate it. This way we can improve the computational cost. Also, my colleague Alex now is working on application of our method for compliance minimization. Thank you everyone for your attention, and please let me know if you have any questions.
Thank you so much, Amin, for your great talk.
Thank
So
you.
now we open the floor for questions for the third presentation. Do we have any question from the audience? Yes, Matthias again.
Sorry, I don't have a question, just a comment. I like very much, really very much these evolution plots with a loss function and these small pictures showing how the physics is respected and so on. I think it was even before it was page 16. Yes, these pictures, they are very insightful, very nice.
Nice. Thank you.
Do we have any other questions, comments? So I don't see any. I think we can move on to the last presentation, right?
Thank you, Naz. Thank you, everyone.
Thank you so much. Shirin, can you share your screen? Presentation mode, please.
Can you hear me?
Yes, but yes.
What about now?
We have some echoes.
No, it's okay.
Yeah.
No, it's okay. Fixed it. Okay. Thank you.
Okay. Can you put it on presentation mode?
Yes.
Yes, great. Yeah.
Everything's fine? Okay.
Yes, great. Our third speaker is Shirin Hosseinmardi. She will be giving a talk on input encoding for operator learning and neural partial differential equation solvers. Shirin Hosseinmardi earned her bachelor's degree in mechanical engineering at the University of Tehran, and she is currently a second-year PhD student in mechanical and aerospace engineering at the University of California, Irvine. Her research is centered on scientific machine learning and data-driven computational mechanics. With that short introduction, the floor is yours and you can start your presentation.
Okay, thank you very much for the introduction. Hello, everyone. I'm Shirin. I'm going to be presenting on another work of our research group. In this work, we've been trying to address some of the shortcomings of neural PDE solvers by proposing a parametric grid convolutional encoder. Our paper is already out. You can check it out. And we also have our code available on GitHub in case you're looking for more details on the implementation side. First, let's talk about why parametric encoding. The main idea behind this is to introduce additional set of trainable parameters besides those of the neural networks, those weights and biases, in an auxiliary data structure like a grid or a graph. And then we would look up and optionally interpolate a subset of those trainable features depending on the input vector. This idea, yet very simple, has shown great promise in some neural rendering applications, computer graphic primitives. Why? Because it offers a trade-off between memory footprint and computational costs, especially in those computationally expensive applications, those tasks found in those neural rendering and computer graphics. And also, it is known for detail preservation. As an example, this paper have demonstrated how they could improve their reconstruction quality when they leverage this parametric encoding compared to the case in which there is no encoding. Now, if we revisit a typical architecture for pins, a simple feed-forward neural network to approximate the solution to the Berger's equation, namely, as Carlos brought up, we see that there is no such mechanism to localize the training, meaning that the same set of trainable parameters would be used to approximate the solution everywhere in the domain. Well, one might argue that we can always locally sample more collocation points, but this is not something intrinsic to the architecture. And what we might be more interested in is having localized parameters, not exactly localized sampled collocation points. We would argue that having this approach, we might be able to address some of the shortcomings known to neural PD solvers or vanilla pins, to be more specific. What are those? Well, the first one is a spectral bias. Spectral bias refers to the tendency of pins or neural networks in general to preferentially learn the lower frequency components of the solution, meaning that, for example, if you look here, at first stages of training, initially the general trend of the target function is learned, and as we proceed with training, we might learn some of the local features, some of the local patterns in the target function. The second issue would be poor information propagation from the boundaries, which basically means that as we get farther away from the boundaries, we may lose some accuracy. And this could be so severe in some cases that we would converge to some incorrect solution irrespective of the boundaries or the initial conditions. Or we might converge to a solution, to the trivial solution. For example, in this case, you see that even though the initial condition is satisfied quite well, so is the periodic boundary condition, the solution has converged to a constant value, which is something less interesting. And you see that the PD residuals seem to be low in this case. And especially in the cases that we do not hard impose the boundary conditions like Carlos does, we're essentially dealing with a multitask learning challenge, meaning that we need to be simultaneously minimizing the PD residual term along with the IC and BC loss term. And as you may know, this could be difficult in some of the problems. So we put the approaches tackling these problems into two broad categories: architectural modifications and training process adaptation. Starting from architectural modifications, we've looked into literature. We have found an instance leveraging this parametric encoding for solving PDEs. The model's name is Pixel. It encodes the input domain by regular Cartesian grids whose vertices are endowed by trainable features. And depending on where the query point is located, 4 feature vectors would be looked up. And then it would perform interpolation. And then it would directly pass those interpolated features to the decoder, which is in their case a relatively shallow feed-forward neural network. I have to say that even though I'm showing a multi-resolution setup here, Pixel actually uses a single resolution because, as I'm going to explain later, they already have too many trainable parameters, and Pixel is quite susceptible to overfitting. So they may not even afford a higher number of trainable parameters here. Speaking of interpolation, this is not a regular bilinear interpolation that you might have thought of, but it is quite similar. Because we need to make sure that the gradients are properly backpropagated, the gradients of those features located at the vertices. We need to achieve C1 continuity at those vertices. And to do so, we need to transform the local coordinates. The local coordinates describe where the point exactly is in an individual cell. We transform those local coordinates, ranging between 0 and 1, by this cosine-based function, and then we would compute the interpolation weights just as we would do in bilinear interpolation. Another thing to mention here is that, as I described earlier, Pixel is susceptible to overfitting, and the way they counteract this is by slightly perturbing their grids, or in other words, they diagonally shift those grids so that the location of the query point with respect to each of those cells would slightly change. Another notable example utilizing a feature space is M4. M4 projects the input space. The input vector here is denoted by zeta. It projects the input space to a high-dimensional feature space by a linear transformation followed by a nonlinear integration function. Here it's a sigmoid. And the features would be referred to as phi1 and phi2 here. And then it would leverage some sort of an attention mechanism to prioritize the features contributing most to solution approximation. Moving on to training process adaptations, most of the works in literature have been trying to balance the contribution of each of those loss terms with respect to the total loss. The criteria, however, is different in each of those works. The one that we adopt is developed by Wang and colleagues. It basically ensures that the gradients of the loss components with respect to the model's parameters, denoted by theta here, have comparable magnitudes. What we do here is, considering the residual term as the reference one, we assign weight 1 to it, and more specifically speaking, we would be computing the lambda hats here, and then we would update the weights denoted by lambda via this moving average form. So if you go back to this figure, instead of just simply summing up the loss components, you would first compute the weights, and then you would do a weighted sum. However, I have to say that PGCAN was developed before NN cores, and if I were to redo it, I would not simply use this. Instead, I would leverage kernels and get rid of the BC and IC loss terms here. This would be much more straightforward, as Carlos described. Having those challenges in mind and inspired by those parametric encoding techniques found in computer graphics applications, now I'd like to introduce our model, Parametric Grid Convolution Attention Network, PGCAN in short. Here's the pipeline. The first thing to note here is that the input vector containing the spatiotemporal coordinates goes both ways here, to the encoder part and to the decoder part. Our encoder shares some similarities with that of Pixel, but Pixel suffers from that issue of poor information propagation inwards. So we tried different things for that. We tried Gaussian averaging of features. We manually assigned weights to those features. But what we ended up using is convolving the features that we have on the grids used for encoding the input space. And applying this convolution, we would no longer have the issue of information propagation inwards. We would have the same grid repetition and shifting mechanism, and then we would do cosine interpolation based on the convolved features as opposed to pixel. And after getting those features, we would split this feature vector into two parts, calling it F1 and F2. The way that we are using those features is kind of similar to how M4 treats phi1 and phi2 their features. So if you remember the formulations, we're simply replacing those phi1 and phi2 by F1 and F2 here, meaning that we're benefiting from the same attention mechanism to prioritize the features that matter most for solution approximation. And during the training, we adaptively, dynamically assign weights to the loss components and proceed with the training for 50K epochs. We studied 4 problems: Berger's, Helmholtz, convection, and lid-driven cavity. You see the reference solutions here. But for lid-driven cavity 1, we are visualizing the velocity magnitude. For the rest, simply U's are visualized. We already know the analytical solutions to Helmholtz and convection, but for Berger's and lid-driven cavity, we're getting the reference solutions by COMSOL. And as you can see, each of these problems have 2 levels of difficulty depending on the parameters that we choose. So we compare PGCAN against 3 baseline models: M4, Pixel, and vanilla pins. We set up the baseline models based on the recommended hyperparameters found in literature. Later, I'm going to talk about what happens if I increase the capacity of each of these models. But looking at this table, we see that PGCAN achieves the best accuracy in many of these problems, except for low viscosity Berger's and low beta convection. However, if you take a closer look, you see that in the cases that we do not achieve the best accuracy, those 2 that I just mentioned, the performance difference is quite marginal. However, in some of the cases that we have the best performance, namely lid-driven cavity, you see that the performance difference is quite substantial. And if you're curious to know how PGCAN will be compared against NN cores, I should say that they were mainly tested on different problems, but in 2 of those problems that we have in common, low viscosity Berger's and low and high Reynolds lid-driven cavity, NN cores would outperform PGCAN in low viscosity Berger's, but PGCAN would have the upper hand in high Reynolds lid-driven cavity problem. Here I am visualizing the error maps. The leftmost column shows the reference solutions, and the other columns show the absolute errors that we get for each of those models. Here are the results for the more complex set of problems. As you can see, in 3 of these, convection, Helmholtz, and LDC, PGCAN is visibly doing better. But in the case of low viscosity burgers, we see that we're not the best achiever, and the errors are mainly concentrated on this vertical line in the middle, where we have this shock-like behavior. It seems that PGCAN is not able to effectively capture these high gradients, and if we naively assume that we know in advance where we may get this problematic behavior, we may have some ways to alleviate this. For example, by locally assigning more features or by refining the cell sizes in that very region. But this is something quite ad hoc, and the very assumption of knowing in advance where we might get those features is something that is not really worth implementing. Here I am showing the performance doing the training for those 50K epochs of training. So as you can see here, in many of these examples, for example, on high beta convection and high frequency Helmholtz, you see that PGCAN offers better accuracy at almost all stages of training. And we had this question: what happens if we increase the number of trainable parameters for each of those baseline models so that they would match PGCAN in terms of the number of trainable parameters? So we tested this on lid-driven cavity problem. You see the figures under the 2 bottom rows, and the dashed curves here would represent the models of roughly the same number of trainable parameters. And as you can see, in some cases, for example, for vanilla pins, you see that we might get some marginal improvements by increasing the size or the capacity, if you will, of the model. However, in the other cases, for example, for M4, high Reynolds lid-driven cavity, the performance would get even worse. So the number of trainable parameters would not directly translate to better performance. We also did the study on features to understand what exactly is being learned in our encoder part. Because what we'd previously seen with Pixel was that the solution itself, or at least its patterns, were captured in the encoder. It wasn't the case for us when we visualized the average feature maps. As you can see here, we see little to no resemblance to the ground truth solution. And when we try to promote such resemblance, meaning that when I try to constrain those features to look like the solution, we got worse results simply because the optimization problem became more complicated. And also, more importantly, the way that we treat those features is totally different from how Pixel treats those features. They directly feed those features into their decoder. However, we project those features onto the intermediate layers of our decoder. So far, we've seen that PGCAN employs regular Cartesian grids for encoding the input domain. However, this does not really restrict us from working on irregular or even 3D geometries. How? Well, all the operations that we have in PGCAN, interpolation and convolution, could be naturally extended to higher dimensions, for example, 3D. And when we are working with an irregular geometry, such as a toroidal domain, this would simply mean that some of the vertices, or equivalently, some of the features, would be located outside the study domain. This would mean that these features would have minimal contribution to the interpolation step that we have in the encoder. So this would not really impact the results that we're going to get at the end. We tested this by solving Poisson equation in a toroidal domain subject to these boundary conditions. And you can see the results here. We are outperforming other baseline models, Pixel, M4, and vanilla pins by 1 to 2 orders of magnitude at almost all stages of training. For this particular case, we're also reporting the cost. You see that PGCAN and Pixel are much more expensive than M4 and vanilla pins in terms of training time. However, I must say that our encoder and also Pixel's encoder are not really implemented in the most optimized way. So we may be able to lower these numbers quite a bit. And as for the number of trainable parameters, we previously studied that we cannot get better accuracies simply by increasing the number of trainable parameters. We might get even worse performances. Earlier in my presentation, I talked about that using that parametric encoding, we might be able to mitigate spectral bias known to pins or neural networks in general. In order to measure this, we use directional PSD pairs. Suppose that we are given square images of size n by n. Just for simplicity, we can perform a 2D Fourier transform zero-centered. We can compute the power spectrum by taking the square of the Fourier amplitudes. We would have some frequencies in x and y direction, and then we can take the average along the other axis. This is how we end up with the directional PSD pairs. However, there's an additional step that we might need to take when we're to compare the frequency components of two signals, just because we're not really interested in the magnitude of those errors. What we can do is to add a constant value to one of those curves to make sure that the two curves would start from the same point. This would enable us to have an easier visual comparison. So we did the same thing for our reference signals. In this figure, you see that the directional PSD curves in x and y direction. For noisy signals, be it Gaussian or uniform, you see that these curves would appear flat in the average sense, of course. But in the signals in which we have dominant frequencies, we would see some peaks in the directional PSD curves. So having a flatter curve would imply lower spectral bias in those particular directions that we're studying. We did the same on our error maps. We treat our error maps as those square images, and then we would compute and plot the directional PSD curves for each of those models across all examples that we solved. You see that in many of these subplots I'm showing here, the blue curve representing PGCAN appears to be the flattest, meaning that there are no dominant frequencies shown in the error maps of that we get for PGCAN in those two directions, x and y. So we can conclude here that PGCAN suffers less from spectral bias compared to other baseline models in those two particular directions. However, that was only a qualitative approach. We can also fit a line to each of those curves and report the slope. We did so and tabulated the results here. You see that in almost all cases, except for low beta convection, PGCAN achieves slopes of the smallest magnitude in x and y direction, again confirming that PGCAN suffers less from spectral bias. Now that we've gauged the potential of PGCAN, we'd like to extend it to topology optimization and operator learning. A colleague of mine, Alex, is now working on extending our topology optimization framework presented by Amin for compliance minimization. Here you can see a classic problem, and the objective function here would be our compliance. These are only preliminary results, but so far what he had observed was that PGCAN is able to better capture high stress concentrations here compared to a simple feed-forward neural network. And as for operator learning, we can think of easy ways to modify our architecture to accommodate operator learning purposes. One easy way would be bringing the input function into our encoder part, particularly the feature convolution block. For example, we can sample the initial conditions in case of Berger's problem, and we can tile an auxiliary grid with those sample points and do this multiplication between the sample points and our trainable grids, and the rest of the model would be the same as before. There might not be any direct analogy between our architecture and typical neural operators out there, DeepNet FNO, but in some sense, our encoder would resemble the branch part of DeepNet because it'll take care of the input functions for us. But we do not have fusion block at the very end just because we project the features capturing the effect of the input function onto the intermediate layers of our network, our decoder. Again, here I'm showing some preliminary results. Carlos already talked about why it is a good idea to have these neural operators as the main function of a GP. So here I'm doing the same. And you can see that we can get competitive results when we have PGCAN plus GP compared to FNO plus GP and DeepNet plus GP. We might not be there yet, especially when the data set is quite small, for smaller ends, I mean. However, these results are seem promising to us. And we tested it on Berger's Dirichlet and our in-house Navier-Stokes problem. By that, I mean the lid-driven cavity problem in which we sweep the domain by smaller windows. Now I'd like to conclude my presentation. First of all, PGCAN offers better accuracy, especially when the complexity of the problem increases. It does not really suffer from spectral bias as much as other baseline models, and for vanilla pins and pixel, as we studied. And it can easily handle 3D regular geometries, just as you saw in the Poisson example solved in a toroidal domain. And we're currently envisioning possible avenues for extending it, namely in topology optimization and operator learning. Thank you for your attention. I'll be happy to take your questions.
Thank you so much, Shirin, for your great talk.
Thank you.
So, do we have any questions for the speaker from the audience?
Yeah, I had a question. This is Varun from Brown. Hi, Shirin. When you talk about projecting the points onto like a regular grid, I was wondering what happens to the size of the grid when you have like more points in one location and less points in some other region of your domain. Does the size of the grid remains the same, or do you have the grid as adaptive? I'm not sure if I understand your method correctly, so maybe if you can like clarify on that.
Yeah, so actually we can take both approaches, right? We can have separate grids, one of binary resolution, the other one of coarser resolution, and then we would concatenate the features obtained by those grids of different resolutions. And we can locally assume that, for example, at one point we have 48 features, but at the other vertex we would have 24 features. Why? Because the way that we use these features by taking the average, okay? And so we can leverage these two mechanisms simultaneously or separately, depending on the problem.
Like suppose you have 2 points which are very close to each other, then you'll probably have like a fine grid there, right? As compared to where you have 2 points which are far away from each other.
Yeah,
in the same
true.
domain.
But our studies show that our current framework is not really sensitive to the resolution. So even though we studied different problems, which visibly had different frequencies, different dominant frequencies, we were using the same resolution for all of those problems because our approach wasn't really sensitive to the resolution. But I agree that in some specific cases, we may need to refine those grids.
Like when you talk about your 3D case, which was like a toroid, generally you have geometries which are, not, you cannot just create like a geometry based on revolving like a 2D shape. In those cases, like you might have much finer, a lot more points around certain features as compared to other features. And in that case, your projected mesh will actually be I'm not able to understand how you will actually do that when you have like varying resolutions in your co-location points, let's say. Is
So
it like you'll have different mesh sizes in different regions? Is that how it will work?
Not really. We do not have any concept like mesh size here because we would have cell sizes. We have consistent cell sizes everywhere in the domain, right? And in those particular geometries that you're mentioning, we might have a lot of redundant features, which would increase our memory footprint. Okay, so our model would become more expensive in terms of the number of trainable parameters. But the thing is, just because those parameters are not really updated during training just because the model would not use them, or they're not contributing as much to the interpolation step that we have in our encoder, they would not really impact the results. But is it the best way to like handle irregular geometries? We have to look into it.
Okay, yeah, thanks.
Do we have any other questions for the speaker? So we don't have more questions. Any comments? Nothing. Thank you so much, Amin, Shirin, and Carlos, for your talk today. I think it's time to close the session. And thank you, everybody, for joining us today. I hope everybody has a great weekend ahead. Bye.
Bye, everyone.
Bye.